Please subscribe to support the channel. What if I told you that we now have the ability to peer almost all the way back to the very beginning of time itself? To gaze into the moment when the first cosmic structures were born, when the first stars began burning, and when the universe itself was still in its infancy. This isn't science fiction, nor is it the plot of a futuristic film. It is happening right now, thanks to one of the most extraordinary scientific instruments humanity has ever built, the James Webb Space Telescope, often called our window into the cosmic past. For thousands of years, human beings have looked up at the night sky, wondering where we came from, how the universe began, and what lies beyond the stars. Ancient civilizations saw the heavens as eternal, infinite, and unchanging. But today, we know the universe has a history. We know it had a beginning, the Big Bang, nearly 13.8 billion years ago. Yet, the question has always lingered: how close can we get to witnessing that beginning with our own eyes? That is where the James Webb Space Telescope, or JWST, comes in. Unlike any telescope before it, JWST is not just a tool for astronomy, it is a kind of time machine. Because light takes time to travel across the cosmos, every time we look far out into space, we are also looking back in time. The farther away the object, the older the light that reaches us. So in a very real sense, when Webb points its golden mirrors into the depths of the universe, it is allowing us to watch the unfolding of history itself. And here's the extraordinary part: JWST has done something no human eye or telescope has ever accomplished before. It has reached farther into the cosmic past than any other observatory. In doing so, it has discovered what appears to be the oldest and most distant galaxy ever observed, a cosmic structure we call JWST Z14-0, or more simply, Z14. This discovery is not just a piece of trivia to be added to the long list of astronomical records. It's a breakthrough that shakes the very foundations of our understanding of how galaxies formed, how quickly they grew, and what the earliest moments of the universe might have looked like. By finding this galaxy, Webb is not only showing us a piece of the past, it is rewriting the story of cosmic origins. So when we ask, what if we could see back almost to the dawn of time? The answer is no longer a matter of imagination. It is reality. With JWST, we are staring directly into the childhood of the universe. When we begin to trace this cosmic journey backward, through the eyes of the James Webb Space Telescope, we find ourselves standing at the edge of one of the most breathtaking revelations in human history. The opening question, what if we could see back almost to the dawn of time, is no longer speculative. It has become tangible. And it is in this context that the discovery of JWST Z14-0, a galaxy that astronomers affectionately call Z14, takes center stage. To appreciate why this discovery matters so deeply, let's first place it within the story of what Webb was built to do. The telescope was designed not just to take beautiful pictures of galaxies and nebulae, but to push the boundaries of how far back in time we can observe. Astronomers always hoped that Webb might show us galaxies within the first few 100 million years after the Big Bang. But what it actually delivered was beyond even the boldest predictions. In the depths of one of Webb's surveys, a project called the JWST Advanced Deep Extragalactic Survey, or JADES, scientists spotted something extraordinary. It was a faint but unmistakable smudge of light, hidden among countless stars and galaxies. At first glance, it looked like many other faint galaxies Webb has detected. But once its properties were analyzed, scientists realized they were looking at something unprecedented, the farthest and oldest galaxy ever confirmed by human instruments. That galaxy is JWST Z14-0, or Z14. Why does the name sound so technical? Let's break it down. The JADES part comes from the name of the survey itself. GS refers to the Great Observatory's Origins Deep Survey South Field, which is a patch of sky chosen because it is relatively dark and free from interference. And the Z14 refers to its redshift value, which essentially measures how far away it is, and therefore, how far back in time we are looking. The higher the redshift number, the older and more distant the galaxy. This galaxy's redshift of around 14 makes it the reigning champion in the cosmic record books. But the name is almost secondary to the story it tells. What really matters is that this faint galaxy is not just another pinprick of light. It is a time capsule, a messenger from an era when the universe was still very young, just a few 100 million years into its existence. To put that in perspective, If we think of the universe's entire 13.8 billion year history as a single 24-hour day, Z14 comes into existence in the first few minutes after midnight. The Milky Way, by comparison, doesn't form until much later in the evening. Scientists have been searching for galaxies from this early period for decades, using telescopes like Hubble to stretch their vision as far back as possible. Hubble did reveal galaxies from the first billion years of cosmic history, but it could never quite reach back into that murky territory closer to the Big Bang. Webb, with its incredible sensitivity in the infrared spectrum, was designed to finally cross that threshold. And with Z14, it has done exactly that. This discovery isn't just about breaking records. Each galaxy we uncover from those early times is like a puzzle piece in the grand story of the cosmos. Z14 is one of the most important pieces yet. It tells us that galaxies were already taking shape very quickly after the Big Bang. It suggests that the universe may have been busier, more dynamic, and more full of light than scientists had previously believed. And it hints at mysteries we don't yet fully understand. How did such a galaxy form so fast? How did it become so bright? What kinds of stars might it contain? Perhaps one of the most striking aspects of this discovery is that it feels almost surreal. For centuries, humans dreamed of glimpsing the universe in its earliest chapters. Today, through this tiny ancient smudge of light captured by JWST, we are seeing not just a galaxy but an echo of creation itself. When the photons from Z14 began their journey across space, Earth did not exist, our Sun had not been born, and the Milky Way had not yet formed. Yet those same photons have traveled for 13.5 billion years to arrive in Webb's detectors, allowing us to finally see them today. That is why astronomers are calling Z14 the most distant and oldest galaxy ever observed. It is not hyperbole. It is a literal crossing of a frontier, a moment in history where humanity's reach has extended farther into the universe's past than ever before. In a way, the discovery of Z14 is a reminder of how remarkable our era is. We are alive at the exact moment in history when our species has developed the tools to look back almost to the dawn of everything. When we talk about Z14, what makes its discovery so breathtaking is not just the fact that it is distant, but the particular place it occupies in the timeline of cosmic history. To understand its importance, we need to situate this galaxy within the chronology of the universe itself, and in doing so, we realize that Z14 is not simply another object catalogued in the sky, but a true milestone in the story of existence. The universe began with the Big Bang around 13.8 billion years ago. In those first instants, there were no galaxies, no stars, no planets, not even atoms as we know them today. There was only a hot, dense sea of particles and energy, expanding and cooling with unimaginable speed. Over time, the first protons and neutrons fused into simple nuclei, eventually giving rise to hydrogen and helium, the most basic building blocks of matter. Yet it would take hundreds of millions of years before gravity could gather those elements into the first stars and galaxies. Now, here's where Z14 comes into focus. The light Webb detected from this galaxy began its journey when the universe was only about 290 million years old. That number might sound enormous in human terms, more than the age of our species, even more than the age of Earth itself, but on the scale of cosmic time, it is practically a newborn. Out of 13.8 billion years, 290 million is just about 2% of the universe's current age. Imagine compressing all of cosmic history into a single calendar year. The Big Bang happens at midnight on January 1st, and today is December 31st, just before midnight. In that analogy, Z14 appears in the very early morning hours of January 2nd. It is almost as close to the beginning as one can get with present-day technology. This is what makes Z14 so extraordinary. It is not merely old, it is primordial. Its light began shining across the cosmos before galaxies like our Milky Way existed, before the first stars in our own neighborhood were even imagined by nature. When the photons we see today were born, space itself was still in the process of becoming transparent after the so-called cosmic dark ages. This was the period when the universe transitioned from being a foggy, opaque soup of particles to a clear, transparent cosmos where light could travel freely. To observe Z14 is to peer into that critical transitional period, the era of reionization, when the first galaxies and stars were transforming the universe from darkness into light. Think about what this means. For the universe to already host a galaxy like Z14 only 290 million years after the Big Bang tells us that galaxy formation happened much faster than astronomers had previously thought. Before Webb, the assumption was that the earliest galaxies would take longer to assemble. We imagined them as faint, tiny patches of stars, struggling to ignite their first generations of light. But Z14, blazing at such an early age, suggests that nature wasted no time at all. Galaxies may have sprung up rapidly, with intense bursts of star formation lighting up the young cosmos sooner than expected. It is almost like discovering that a baby has already learned to walk when we thought it should still be crawling. The existence of Z14 at such an early time challenges the models astronomers have relied on for decades. It asks us to rethink how quickly stars formed, how efficiently matter gathered together under gravity, and how the cosmic web of galaxies wove itself into being. And here is another astonishing layer: the time it took for Z14's light to reach us. Those photons traveled across 13.5 billion years of cosmic expansion. Along the way, space itself stretched, dragging the light into longer and redder wavelengths until Webb's sensitive infrared eyes could catch them. What we are seeing, then, is not just a picture of a faraway galaxy. It is a living snapshot of the universe's own childhood, a time so remote that even our imaginations struggle to capture it. When we say the universe was 2% of its current age at the moment Z14 existed, it forces us to zoom out in our perspective. Everything we know today, the formation of the Milky Way, the birth of the Sun and Earth, the evolution of life, the rise of human civilization, all of this is compressed into the final 98% of the cosmic timeline. Z14 represents the moment just after the curtain first rose on that grand stage. It is the prologue to everything. And yet, despite its youth, Z14 is not shy. It shines brighter and appears larger than many astronomers predicted for such an early epoch. It is as though the universe wanted to announce its own story loudly, ensuring that when we finally develop the tools to look back this far, we would not miss it. So when we say Z14 existed just 290 million years after the Big Bang, we are not only marking its place on the calendar of the cosmos. We are acknowledging that this little smudge of light has bridged nearly the entire history of reality to reach us. It stands as both a relic of unimaginable antiquity and a messenger carrying the whispers of creation itself. What makes Z14 so profoundly special is not just the fact that it exists, but the astonishing journey its light has taken to reach us. When we gaze at this galaxy through the James Webb Space Telescope, we are not simply observing a distant object. We are catching the faintest echoes of a cosmic message that has been traveling across the vast abyss of space and time for 13.5 billion years. That is almost the entire lifetime of the universe itself. Consider the scale of that journey for a moment. Light is the fastest thing in the universe. It races along at 300,000 kilometers per second, fast enough to circle the Earth more than 7 times in a single second. In human terms, it takes just over a second for a radio signal to travel from Earth to the Moon. It takes about 8 minutes for sunlight to reach us across the 150 million kilometers of space between our planet and the Sun. But the photons we are now receiving from Z14 have traveled across 13.5 billion years of cosmic expansion. They have endured a voyage so long that entire galaxies have formed, evolved, and died during their journey. That alone is staggering, but the significance of Z14 goes deeper. Before Webb, the farthest confirmed galaxies came from earlier record holders like Z13 and Z12, galaxies also spotted by JWST but slightly closer to us in time. Each new discovery has pushed the boundary back a little farther, peeling away another layer of the universe's ancient history. But Z14 has smashed through those previous records, making it not only the most distant galaxy confirmed but also the most reliable and robust measurement of such a young cosmic structure. The reason this is such a breakthrough is because every new oldest galaxy tells us something critical about the early universe. Z14 shows that massive, bright galaxies were forming much earlier than we thought. This was not expected. For decades, astronomers assumed that the earliest galaxies should be faint and fragile, composed of just a few stars slowly gathering into clusters. Yet Z14 shines like a beacon across billions of years, far brighter than our models had predicted for something born so soon after the Big Bang. Its very existence forces us to rethink the speed at which galaxies can assemble. This brightness also tells us something profound about the nature of its stars. To produce that much light in such a short amount of time, Z14 must have experienced an incredible burst of star formation. Some of those stars may have been among the mysterious population 3 stars, the first stars ever created, forged from pure hydrogen and helium, unpolluted by heavier elements. These stars were thought to be enormous, short-lived, and intensely luminous. If Z14 indeed contains them, then Webb may have brought us closer than ever to witnessing the very first generation of stars that illuminated the universe. And it isn't just the brightness that makes Z14 remarkable, it is also its sheer endurance as a cosmic time traveler. Those photons that began their journey just 290 million years after the Big Bang have been stretched and distorted along the way by the expansion of space itself. The effect, known as redshift, has shifted their light into the infrared spectrum, making them invisible to human eyes and even to older telescopes like Hubble. Only JWST, with its incredible sensitivity to infrared wavelengths, could finally reveal them. Without Webb, Z14 would still be hiding in the darkness, unknown and unseen. This is why Z14 is not just a record breaker but a landmark in our exploration of the universe. It is proof that our tools have reached the level where we can study galaxies almost as soon as they emerged. It tells us that the universe is more complex, more dynamic, and more filled with surprises than we had dared to dream. And perhaps most importantly, it shows that the story of cosmic dawn, the first moments when the universe began to shine, is within our reach to explore in detail. What truly elevates Z14 above the previous record holders is the certainty of its detection. Earlier candidates for the oldest galaxy sometimes left room for doubt. Was the light really from a distant galaxy, or was it from something closer that happened to mimic the signal? In the case of Z14, Webb's spectroscopic instruments confirmed its redshift beyond reasonable question. This makes Z14 not just the farthest galaxy we have ever observed, but the most trustworthy window into that ancient past. It is no exaggeration to say that Z14 stands as the best evidence yet of humanity's ability to look back nearly to the dawn of time itself. Imagine what this means for our perspective as human beings. On a personal level, we live fleeting lives that last perhaps a century if we are fortunate. Yet through the lens of JWST, we can glimpse an object that has outlived countless generations, civilizations, and even entire epochs of cosmic history. Z14 is a silent witness to nearly the entire age of the universe, its light carrying secrets from a time when reality itself was still taking shape. To see it now is to bridge the deepest divide imaginable, the gulf between the present moment and the near beginning of everything. That is what makes Z14 remarkable. Its light has traveled almost the full length of cosmic history. It has broken records, challenged theories, and given us a vision of the universe in its raw, untested youth. In that faint glow, preserved across 13.5 billion years, lies a reminder that our story is part of something far larger than ourselves. A story that began long before we arrived, and one that will continue long after we are gone. The discovery of Z14 was remarkable not only for its age and distance, but also for the story it seems to tell about the earliest generations of galaxies. Among astronomers and astrophysicists, it has affectionately earned the nickname MOM Z14, a term that may sound whimsical at first but carries profound meaning. This is not merely a playful moniker. It reflects the galaxy's potential role as a kind of cosmic progenitor, a mother from which many aspects of later galactic evolution could trace their origins. Why MOM? The idea stems from what Z14 represents in the context of cosmic history. As the earliest galaxy detected with such certainty, it may be among the first galaxies to have formed in the universe. In other words, it could be a direct descendant of the very first star-forming regions, and in this sense, it acts as a kind of ancestor or maternal figure to the myriad galaxies that followed. Just as a mother carries the genetic blueprint for future generations, Z14 may carry the fundamental patterns, chemical compositions, and structures that shaped subsequent generations of galaxies. Studying it could reveal the family tree of cosmic evolution. Galaxies are not static objects. They grow, merge, and evolve over billions of years. The earliest galaxies, like Z14, are particularly important because they set the stage for everything that comes afterward. By understanding Z14, astronomers can start to unravel how the universe went from a simple cloud of hydrogen and helium into the rich and complex tapestry of stars, galaxies, and clusters we see today. In that sense, Z14 is a kind of archetype, a blueprint for galaxy formation. If it is among the first fully realized galaxies, It might have nurtured the processes that eventually gave rise to larger galaxies like the Milky Way. Hence the nickname MOM Z14 resonates on both a scientific and symbolic level. The maternal analogy also extends to the galaxy's potential to harbor the earliest generations of stars, the so-called population 3 stars. These stars are believed to be the very first to have formed in the universe, composed almost entirely of hydrogen and helium, unpolluted by heavier elements created in later stellar generations. If Z14 contains such primordial stars, it is not just a mother in a metaphorical sense. It may literally be the cosmic nursery from which the earliest stars emerged. These first stars, in turn, seeded the universe with the elements necessary to form subsequent generations of stars, planets, and ultimately life itself. Z14, in this view, is a key participant in the chain of cosmic motherhood that led to the universe as we know it. Astronomers are particularly excited because observing MOM Z14 allows them to investigate the early stages of galaxy assembly. Its existence so early in the universe's history suggests that galaxies may have formed faster than previously believed. This galaxy could contain clues about how stars clustered together in those first 300 million years, how galaxies accumulated mass, and how the first light sources helped end the cosmic dark ages. In effect, MOM Z14 could be the Rosetta Stone of early galaxy formation, a rare, accessible key to decoding processes that would otherwise remain hidden in the distant past. The nickname also reflects the sense of awe and humility that astronomers feel when contemplating Z14. Unlike many other discoveries that are exciting for their novelty, MOM Z14 inspires wonder because it connects us to the universe's origins in a very personal way. By peering at this galaxy, scientists are not just observing an astronomical object, they are tracing a lineage, seeing the mother of all galaxies in action, and witnessing the processes that eventually gave rise to cosmic structures we inhabit billions of years later. The affectionate term is also a reminder that science is a human endeavor. While the data and spectra provide rigorous evidence, the names we give to discoveries often reflect the emotional resonance they hold for us. In calling this galaxy MOM Z14, astronomers acknowledge that we are looking at something nurturing and formative, a foundational entity in the cosmic story. It bridges the gap between complex scientific phenomena and a narrative that humans can grasp intuitively. The universe has its own kind of parenthood, its own origins, and we are fortunate enough to observe it. In a very real sense, MOM Z14 is both literal and symbolic. Literally, it is one of the earliest galaxies ever formed, likely hosting the first generations of stars. Symbolically, it represents the concept of a mother in the cosmic sense, the source from which later galaxies and star systems may have emerged. This dual significance makes it one of the most captivating discoveries in modern astronomy. Every observation of MOM Z14 provides a window into how the universe's first structures formed, how they grew, and how they ultimately shaped the universe we see today. By thinking of Z14 as a mother galaxy, we begin to see the universe not just as a collection of isolated objects but as a connected, evolving system. Each galaxy carries a history, a genealogy of matter and energy, and MOM Z14 may represent the very root of that tree. Observing it allows us to witness the universe's infancy and to explore the formative processes that made all later galaxies, including our own Milky Way, possible. The story of MOM Z14's discovery is as much about human ingenuity as it is about the galaxy itself. Without the extraordinary capabilities of the James Webb Space Telescope, this galaxy would still be lost in the cosmic darkness, invisible to every instrument that came before it. To truly appreciate how astronomers were able to uncover MOM Z14, we must delve into the technology and techniques that made this monumental observation possible, particularly focusing on the near-infrared camera, or NIRCam, one of Webb's most powerful instruments. Webb was designed to see the universe in infrared light, which is crucial when studying the earliest galaxies. As the universe expands, light from distant objects gets stretched, a phenomenon called redshift. Light that started out as visible or ultraviolet is elongated into the infrared spectrum by the time it reaches Earth. Traditional optical telescopes like Hubble, which excel in visible light, are simply not sensitive enough to detect this stretched radiation from galaxies as distant as MOM Z14. Infrared vision is essential to seeing the faint glow of these ancient cosmic structures, and that is where NIRCam comes in. NIRCam functions like an incredibly sensitive infrared eye. It can detect extremely faint light and split it into multiple wavelengths simultaneously, allowing astronomers to measure the galaxy's brightness across different parts of the spectrum. By doing this, scientists can begin to identify which signals come from high redshift galaxies and which are foreground objects or noise. Essentially, NIRCam is scanning the sky for tiny differences in color and intensity that indicate the presence of galaxies that existed billions of years ago. When observing the patch of sky where MOM-Z14 resides, NIRCam detected a faint, red-tinged source of light. At first glance, it looked like any other faint galaxy dotting the cosmic field. But the pattern of light across the various infrared filters revealed something remarkable. This object was missing in certain shorter wavelength filters but appeared clearly in the longer wavelength ones. This drop-off in brightness at shorter wavelengths is a telltale sign of extreme redshift, indicating that the galaxy's light had been stretched significantly due to the universe's expansion. In simpler terms, the farther away a galaxy is, the more its light shifts toward the red end of the spectrum. NIRCam sensitivity allowed astronomers to notice this subtle shift, signaling that they were looking at a galaxy from an era almost 13.5 billion years ago. But NIRCam's role went beyond simply detecting the galaxy. By measuring the intensity of light across multiple infrared filters, astronomers could construct a preliminary estimate of its redshift, providing a first hint that this object might be MOM-Z14. This process is akin to using color-coded clues to triangulate the distance of a distant fire on the horizon. The redder the signal, the farther and older the object. NIRCam's precise measurements provided the first concrete evidence that this faint smudge was not just any distant galaxy but potentially the oldest one ever observed. The discovery process was meticulous. Webb does not take casual snapshots. Instead, it gathers deep, long exposures of carefully selected regions of the sky. The JADE survey aimed its instruments at a specific patch of space known for being relatively free from foreground interference, allowing faint objects like MOM-Z14 to be detected without contamination from nearby stars or galaxies. NIRCam collected light over many hours, sometimes even days, building up a picture of extremely faint sources. Without this accumulation of photons, MOM-Z14 would have been far too faint to identify. Once NIRCam highlighted the candidate, astronomers then moved to confirm its identity using Webb's other instruments, such as its spectrographs. But it was the initial detection by NIRCam that made everything possible. Without this sophisticated infrared imaging, MOM-Z14 would remain just a theoretical possibility, a distant whisper in the vast cosmic void. NIRCam turned that whisper into a detectable signal, giving scientists the evidence they needed to pursue further confirmation. What makes this even more impressive is the level of precision required. We are talking about an object whose light is incredibly faint, billions of times dimmer than what we could see with the naked eye, even if we had perfect vision. NIRCam had to distinguish it from the background noise of the universe, the infrared glow of other sources, and the thermal emissions from the telescope itself. The fact that Webb could achieve this at such extreme distances is a testament to decades of technological development, engineering brilliance, and careful planning by hundreds of scientists and engineers. Through NIRCam, astronomers were able to transform a tiny, almost imperceptible signal into a meaningful cosmic discovery. The detection of MOM-Z14 is a story of patience, precision, and cutting-edge science. A demonstration of how the right tool, pointed at the right place, can reveal something the universe has hidden for nearly the entirety of its history. In that faint red light, NIRCam not only discovered a galaxy, it uncovered a relic of the cosmic dawn, a window into the universe's formative years. To truly grasp why NIRCam was able to detect MOM-Z14, we need to understand the concept that makes it possible to measure such vast distances: redshift. At first, redshift might sound like an abstract astronomical term, but in reality, it is a simple phenomenon rooted in the way light travels across an expanding universe. By breaking it down, we can see why this tiny smudge of light tells us so much about the universe's earliest days. Imagine you are standing on a sidewalk as an ambulance speeds past you with its siren blaring. As it approaches, the sound waves are compressed, making the siren pitch higher. As it moves away, the sound waves stretch out, and the pitch drops. This is called the Doppler effect, and it is a familiar experience in everyday life. Redshift works in much the same way, but instead of sound waves, we are talking about light waves, and instead of cars, we are talking about galaxies moving away from us as the universe expands. The universe is not static. It has been expanding ever since the Big Bang. This expansion stretches the fabric of space itself. When a galaxy is far away, the light it emits has to travel through this stretching space to reach us. The longer the light travels, the more it gets stretched. Because light waves have a wavelength, the distance between one peak of a wave and the next, stretching them moves them toward the red end of the spectrum, which is why we call it redshift. In other words, distant galaxies appear redder than they would if they were nearby, and the farther they are, the redder they appear. For astronomers, measuring this redshift is like reading a cosmic ruler. By observing how much the light from a galaxy has shifted toward the red, scientists can determine how far away it is and, crucially, how long the light has been traveling. In the case of MOMZ-14, the light has been traveling for an astonishing 13.5 billion years. Its extreme redshift tells us not only that it is incredibly distant but also that we are seeing it as it was when the universe was only about 290 million years old. Without redshift, we would have no way of distinguishing this faint signal from the countless other objects in the sky. Redshift also explains why MOMZ-14 is visible in infrared light rather than in the visible spectrum. Light that left the galaxy originally may have been in the ultraviolet or visible range, the kind of light emitted by young, hot stars. But because the universe has expanded so dramatically over billions of years, the wavelength of that light has been stretched so far that it now falls in the infrared portion of the spectrum. This is why JWST's infrared capabilities are essential. Without them, we wouldn't be able to detect these earliest galaxies at all. The concept can also be illustrated by thinking of a balloon with dots drawn on it. If you inflate the balloon, the dots move farther apart, and the space between them stretches. In the same way, as the universe expands, the light traveling across it stretches, producing a redshift that we can measure. The farther a galaxy is from us, the more its light has been stretched, and the higher its redshift. MOMZ-14 has one of the highest redshifts ever measured, which is why it represents the oldest galaxy we have detected with confidence. Redshift is not just about measuring distance, it is a window into time itself. By determining a galaxy's redshift, astronomers can calculate when the light left that galaxy and, by extension, what the universe looked like at that moment. With MOMZ-14, the extreme redshift tells us we are seeing the universe almost as soon as it emerged from the cosmic dark ages, when the first stars and galaxies were beginning to shine, lighting up a cosmos that had been dark for hundreds of millions of years. In short, redshift is the universe's way of telling us its history. It allows astronomers to look across vast distances and unlock the timeline of cosmic evolution. Without understanding and measuring redshift, the discovery of MOMZ-14 would be meaningless. It would just be another feint in the sky. Redshift transforms that into a living story from the universe's infancy, connecting us directly to the time when the very first galaxies were forming. Detecting MOMZ-14 with an IRCam was only the first, crucial step. While the faint infrared glow suggested a galaxy of incredible age and distance, astronomers needed confirmation to ensure they were truly seeing one of the universe's earliest galaxies. Initial imaging alone, though tantalizing, cannot prove the exact distance of such a distant object. That is where JWST's spectrograph instruments came into play, transforming what was a promising candidate into a definitive cosmic landmark. Spectrographs are essentially cosmic prisms. While cameras capture images of light, spectrographs split that light into its component wavelengths, creating a spectrum. This spectrum acts like a barcode for the galaxy, revealing details about its chemical composition, temperature, motion, and, most critically for MOMZ-14, its redshift. By analyzing the pattern of absorption and emission lines in the spectrum, astronomers can measure exactly how much the light has been stretched due to the expansion of the universe. This allows them to calculate the galaxy's distance with far greater precision than imaging alone can provide. In the case of MOMZ-14, JWST used its near-infrared spectrograph, NIR-SPEC, and other spectroscopic instruments to observe the galaxy in detail. When scientists examined the spectrum, they found characteristic signatures of hydrogen and helium, as well as subtle hints of heavier elements, all shifted toward longer wavelengths. The amount of redshift detected in these spectral lines corresponded precisely to the extraordinary distance implied by the initial NIR-CAM imaging. This confirmed that MOMZ-14's light had been traveling for approximately 13.5 billion years and that we were observing the galaxy as it existed just 290 million years after the Big Bang. This spectroscopic confirmation is what sets MOM-Z14 apart from previous candidate galaxies. In the past, astronomers sometimes detected extremely faint objects with colors suggesting high redshifts, but without spectroscopy, there was always uncertainty. Some candidates turned out to be closer galaxies or other cosmic phenomena masquerading as distant objects. MOM-Z14, however, is different. The combination of NIR-CAM imaging and NIR-SPEC spectroscopy provides robust, multilayered evidence, making it the most reliable and well-validated ancient galaxy yet discovered. It is not just a promising lead, it is a cosmic certainty. Spectroscopy also provides a window into the galaxy's physical characteristics. By analyzing the light in detail, astronomers can infer how quickly stars were forming, how bright they were, and how the galaxy might have evolved over time. For MOM-Z14, the spectroscopic data revealed that it is surprisingly bright for such an early galaxy, hinting at intense star formation and the possible presence of population 3 stars, the first generation of stars born in the universe. This level of detail would have been impossible to achieve with imaging alone, underscoring the critical role of JWST spectrographs in turning a faint red smudge into a richly informative cosmic discovery. The process of confirmation also involved careful cross-checking. Scientists compared the spectrum of MOM-Z14 against models of galaxy formation and stellar populations to ensure that the features observed matched what would be expected for a galaxy at such a high redshift. Every line in the spectrum, every tiny shift in wavelength, had to make sense in the context of the universe's expansion history. The result was a resounding validation. MOM-Z14 is indeed the oldest, most distant galaxy ever observed with such certainty. This level of reliability is more than just a technical achievement. It means that astronomers can now use MOM-Z14 as a cornerstone for understanding the early universe. Previous discoveries of high redshift galaxies, while groundbreaking, were often treated with caution because of potential uncertainties. MOM-Z14, however, is a benchmark, a reference point for studying how galaxies formed and evolved in the first few 100 million years after the Big Bang. It gives scientists confidence that their models of cosmic history can be anchored in real, observable data from the universe's infancy. In essence, the spectrographic confirmation of MOM-Z14 turns it from a tantalizing possibility into a verified cosmic landmark. We are no longer speculating about what the universe might have looked like shortly after the Big Bang. We are seeing it, measuring it, and analyzing it in unprecedented detail. This is what makes MOM-Z14 so transformative. It is not just another galaxy among billions. It is a direct, reliable window into the universe's earliest epoch, bridging the gap between theory and observation in a way that was unimaginable just a few years ago. When astronomers finally laid eyes on MOM-Z14 through the lens of JWST, the galaxy's appearance was both astonishing and confounding. Based on decades of theoretical models and observations of other early galaxies, scientists expected the universe's first galaxies to be small, faint, and irregularly shaped, more like scattered clumps of stars than fully formed galaxies. After all, they were thought to be just beginning to coalesce out of primordial gas clouds. MOM-Z14, however, defied these expectations on multiple fronts. For starters, it is surprisingly bright. Despite existing only 290 million years after the Big Bang, the galaxy shines with an intensity that suggests rapid and prolific star formation. The light captured by JWST's NIR-CAM indicates that a significant number of stars had already formed within this young galaxy, creating a luminosity far beyond what astronomers predicted for galaxies in the universe's first few 100 million years. Its glow is strong enough to stand out against the faint background of countless other distant galaxies, signaling that something extraordinary is happening within it. In addition to its brightness, MOM-Z14 is larger than anticipated. Early galaxy formation models suggested that galaxies emerging at such a high redshift would be tiny, perhaps only a fraction of the size of modern galaxies like the Milky Way. Instead, MOM-Z14 exhibits a spatial extent that is unusually substantial for its epoch. This challenges the conventional wisdom that the earliest galaxies were mere building blocks, slowly merging over time to create larger structures. MOM-Z14 demonstrates that the processes governing galaxy growth could be far more efficient than previously thought, allowing massive collections of stars and gas to form quickly in the primordial universe. Its structure is also noteworthy. While the resolution of even JWST cannot reveal fine details of individual stars at such extreme distances, the galaxy shows signs of coherence and organization. It is not a chaotic, scattered blob but appears relatively well assembled, indicating that the forces shaping galaxies, gravity, star formation, and gas dynamics, were already operating efficiently in these earliest cosmic epochs. The galaxy may even contain denser clumps of stars where star formation is particularly intense, possibly including population 3 stars, the first stars ever born. This structural maturity was unexpected. It suggests that galaxies could evolve more rapidly than models had assumed, forming organized systems almost immediately after the universe transitioned from the cosmic dark ages. The contrast between expectation and reality makes MOM Z14 particularly fascinating. The assumption had been that the first galaxies would be difficult to observe, dim points of light requiring long exposure times and careful analysis to even confirm their presence. MOM Z14, by contrast, is relatively luminous and well-defined, providing astronomers with a clear window into the processes of early galaxy formation. Its brightness also makes it a prime target for spectroscopic studies, allowing instruments like NIR-SPEC to analyze its chemical composition and gain insight into the universe's first stars and star clusters. Another intriguing aspect of MOM Z14's appearance is how it reshapes our understanding of cosmic chronology. A galaxy of this size and luminosity forming so early implies that star formation and galaxy assembly occurred at a remarkable pace. The mechanisms that drive these processes, gravitational collapse, cooling of primordial gas, and early stellar feedback, must have been extraordinarily efficient. Observing a galaxy that is both large and bright at this epoch provides a unique laboratory to test our theories of early cosmic evolution and refine our models for how galaxies grow. Moreover, MOM Z14 serves as a visual bridge between the early universe and the galaxies we see today. Its surprisingly mature characteristics suggest that the foundations of galactic architecture, from star clusters to nascent spiral structures, could be set extremely early in cosmic history. By studying its appearance, astronomers can infer how the first galaxies might have seeded later generations, offering a direct glimpse into the lineage of cosmic evolution that eventually gave rise to galaxies like our Milky Way. The galaxy's luminous and sizable nature is also crucial for public engagement and scientific imagination. Images and renderings of MOM Z14 inspire, or not only because of the technical achievement involved in observing it, but also because it challenges our intuitions about the early universe. It prompts a re-evaluation of how fast the universe could organize itself, how quickly stars could form, and how the earliest galaxies might have looked in ways that textbooks had not fully anticipated. In essence, MOM Z14 is a beacon from the dawn of time. Its brightness, size, and relative structural maturity make it more than a distant speck in the sky. It is a vivid, tangible record of the universe's formative years. Every photon captured from this galaxy offers insight into a time when the cosmos was awakening, when the first stars ignited, and when the earliest galactic structures began to emerge. Observing its appearance allows us not just to confirm its existence, but to begin deciphering the processes that built the universe itself. MOM Z14 is not just remarkable for being the oldest galaxy ever observed. It is a genuine surprise in the most fundamental sense. For decades, astronomers have developed theoretical models of how galaxies form and evolve, especially in the universe's earliest epochs. These models were based on our understanding of physics, cosmology, and observations of slightly later galaxies. They painted a picture of the first galaxies as small, faint, and fragile structures, gradually coalescing from clouds of primordial gas over hundreds of millions of years. MOM Z14, however, refuses to fit into this neat theoretical framework. The prevailing expectation was that in the universe's first 300 million years, galaxies would resemble scattered star clusters rather than cohesive systems. Gravity would begin pulling together hydrogen and helium, and the first stars would ignite in isolated pockets. The light from these nascent stars would be dim, diffuse, and challenging to detect, even with the most sensitive instruments. Essentially, astronomers thought the earliest galaxies were cosmic infants, tiny, scattered, and barely visible. MOM Z14 defies that expectation. Instead of being small and dim, it is surprisingly bright and relatively large, almost fully assembled for a galaxy that existed just 290 million years after the Big Bang. Its brightness indicates rapid and substantial star formation, while its size suggests that gas and stars had already gathered into a coherent structure, defying the assumption that galaxies needed hundreds of millions of years to grow. In other words, MOM-Z14 appears far more mature than cosmologists predicted for its age. This discrepancy challenges the fundamental assumptions about early cosmic evolution. If galaxies could reach such a level of development so quickly, it implies that the processes driving galaxy formation were far more efficient than current models had anticipated. Perhaps star formation in the early universe occurred in intense bursts, or maybe primordial galaxies were able to accumulate mass faster due to higher gas densities or other environmental factors. Whatever the cause, MOM-Z14 forces astronomers to revisit the timelines and mechanisms they had long assumed were universal. Moreover, its maturity raises questions about the first generations of stars. The galaxy's luminosity hints that it may contain population 3 stars, the first stars ever born, which are theorized to be enormous, hot, and short-lived. The presence of such stars would explain the intense brightness of MOM-Z14, yet it also challenges models about how quickly such stars could form and how they influenced early galaxy evolution. If these early stars existed in large numbers and burned brightly, it might explain why MOM-Z14 appears so well developed so soon after the Big Bang. Another surprising aspect is its structural coherence. Many early galaxies observed in the past, especially at slightly lower redshifts, appear irregular or clumpy, reflecting the gradual assembly of stars and gas. MOM-Z14, however, shows signs of a more organized structure, suggesting that the processes shaping galaxy morphology, the arrangement of stars, clusters, and gas, were already in place far earlier than previously thought. This indicates that even at such a young age, the universe had mechanisms capable of producing galaxies that were not chaotic blobs but structured systems capable of sustaining rapid star formation. The implications of this surprise extend to our broader understanding of cosmology. If MOM-Z14 is representative of galaxies at similar redshifts, then the early universe was a far more dynamic and productive place than our models predicted. It raises questions about the efficiency of gas cooling, the speed of star formation, and the role of dark matter in assembling early galaxies. Essentially, the galaxy is a direct challenge to theoretical expectations, forcing scientists to refine their models and perhaps consider entirely new processes that could explain such rapid development. This surprise also emphasizes the importance of JWST. Until now, astronomers could only speculate about the earliest galaxies based on fainter, less precise observations from Hubble or other telescopes. JWST's ability to detect and characterize MOM-Z14 provides empirical evidence that the universe can be far more prolific at its dawn than anyone imagined. Each photon from this galaxy acts as a counterexample to old theories, demanding that models accommodate galaxies that are both bright and large in the first few 100 million years. In essence, MOM-Z14 is a cosmic rebel. It refuses to follow the predictions laid out by decades of cosmological theory, forcing astronomers to rethink what they know about the early universe. Its brightness, size, and apparent maturity suggest that the first galaxies may have formed faster, more efficiently, and more dynamically than previously believed. This makes it not just a record-breaking discovery, but a transformative one, reshaping our understanding of the universe's formative years and opening new avenues for research into the origins of galaxies, stars, and cosmic structures. The discovery of MOM-Z14 is more than just a record-breaking observation. It is a paradigm-shifting revelation for cosmology. Until now, scientists believed that the universe's first galaxies formed gradually, over hundreds of millions of years, slowly accumulating stars and gas before coalescing into structures large enough to be visible across cosmic distances. Models predicted a universe where the first galaxies were tiny, dim, and fragile, struggling to shine in the darkness of the cosmic dawn. MOM-Z14, however, turns that picture on its head. Its existence just 290 million years after the Big Bang demonstrates that galaxy formation could occur far more rapidly than previously imagined, reshaping our understanding of the timeline and mechanics of the early universe. The sheer size and brightness of MOM-Z14 suggest that the processes governing galaxy formation, such as gas accumulation, star formation, and gravitational assembly, were already highly efficient at an extremely early stage. In traditional models, the first galaxies were expected to be small building blocks that merged slowly over hundreds of millions of years to form larger systems. MOM-Z14, however, indicates that fully formed galaxies, with substantial star populations and coherent structures, were already present in the universe's infancy. This challenges long-held assumptions about the pace of cosmic evolution and implies that galaxies could grow and mature much faster than our simulations had predicted. This finding also raises profound questions about the physics of the early universe. How did gas cool and condense into stars so quickly? Were the earliest star formation episodes more intense than previously believed, with bursts of star creation producing massive clusters in a short period? Did dark matter, which underpins the gravitational scaffolding of galaxies, play a role in accelerating these early growth processes more efficiently than anticipated? MOM-Z14 provides a concrete example that pushes cosmologists to revisit these fundamental questions and refine their models to accommodate rapid galactic growth. Additionally, MOM-Z14's discovery affects our understanding of the epoch of reionization, the period when the first stars and galaxies ionize the surrounding neutral hydrogen, transforming the universe from opaque to transparent. The brightness and size of MOM-Z14 imply that early galaxies could have contributed significantly to this reionization process sooner than expected. If galaxies like MOM-Z14 were common in the early universe, it suggests that the cosmic dark ages may have ended faster, and the universe's first light could have spread more rapidly across space. This has a direct impact on our models of how the universe became transparent to radiation and how subsequent generations of stars and galaxies formed in that environment. MOM-Z14 also provides a benchmark for testing theoretical models of galaxy formation. For decades, cosmologists have relied on simulations to predict what the earliest galaxies should look like. These models were constrained by the limits of previous observations, which rarely reached beyond a redshift of 10 or 11. With MOM-Z14 at a redshift of 14, astronomers now have a data point from a far earlier time than ever before. This allows for calibration of models, offering a concrete example of what galaxies at extreme redshift can look like, their luminosity, structure, and potential stellar populations. It essentially gives cosmologists a window into the formative processes of the universe, providing the first empirical evidence of how rapidly galaxies could assemble in the first few 100 million years. The implications extend even further. If MOM-Z14 is representative of a population of early galaxies, it may indicate that the universe was far more active in its infancy than previously thought. Instead of a slow, gradual buildup of cosmic structure, the early universe may have experienced intense periods of star formation, with galaxies forming in bursts and quickly reaching sizes and brightness levels that were previously considered impossible. This challenges not just galaxy formation theories but also our understanding of early star formation, chemical enrichment, and the evolution of cosmic structures on the largest scales. Furthermore, the discovery of MOM-Z14 influences the way astronomers approach future observations. Now that we know fully formed, bright galaxies existed so early, it motivates deeper and more targeted surveys with JWST and other instruments. Scientists will be searching for more galaxies like MOM-Z14, looking to determine whether it is an outlier or part of a more widespread early population. Each new discovery has the potential to further refine, or even rewrite, our understanding of how the universe evolved in its first few 100 million years. In a broader sense, MOM-Z14 reshapes our cosmic perspective. It demonstrates that the universe became structured, luminous, and complex much faster than previously imagined. The discovery forces cosmologists to confront the idea that the first galaxies were not just isolated pockets of light, but potentially large, bright, and dynamically active systems that played a significant role in shaping the universe we inhabit today. By providing a direct glimpse into the universe's formative years, MOM-Z14 transforms abstract theories into observable reality, bridging the gap between prediction and proof. Before the discovery of MOM-Z14, astronomers were already pushing the limits of what we could observe in the early universe. Galaxies like Z12 and Z13, previously detected by JWST in earlier surveys, held the record for the most distant, ancient galaxies known to science. These galaxies were remarkable in their own right, each providing glimpses of the universe within the first 400 to 500 million years after the Big Bang. They were milestones that expanded the boundaries of our understanding, offering tantalizing insights into the earliest epochs of galaxy formation. Z12, for instance, was celebrated as one of the first galaxies detected at extreme redshift with JWST. Its discovery proved that massive, star-forming galaxies existed much earlier than many cosmological models predicted. Its light had been traveling for roughly 13.4 billion years, showing us a universe that was still in its infancy. Observing Z12 provided critical data on early star formation and helped astronomers refine their models of how the first galaxies assembled. It was considered an extraordinary achievement, confirming that our observational technology had finally caught up to the theory of galaxy formation. Z13 followed shortly after, pushing the frontier even further. Its detection hinted at a universe alive with activity much earlier than Hubble could ever reveal. Z13 demonstrated that galaxies could form, grow, and shine brightly just a few 100 million years after the Big Bang. These discoveries were vital in building the narrative of cosmic evolution, each new high-redshift galaxy refining our understanding of how quickly stars and galaxies emerged from the primordial universe. They were landmarks, but they also left lingering questions. Could galaxies form even earlier? How bright and massive could these first galaxies be? Enter MOM Z14. Its discovery didn't just add another galaxy to the roster, it shattered previous records. With a redshift around 14, it surpasses Z13 and Z12, firmly establishing itself as the oldest and most distant galaxy confirmed to date. Its light has been traveling for roughly 13.5 billion years, and it represents a snapshot of the universe at a time when cosmic structures were barely beginning to form. By eclipsing the record held by Z13 and Z12, MOM Z14 provides a new benchmark for what is possible in the early universe, demonstrating that galaxies could exist, shine, and even thrive far earlier than previously thought. This progression, from Z12 to Z13, and now to Z14, illustrates not only the extraordinary capabilities of JWST but also the accelerating pace at which our understanding of the early universe is evolving. Each discovery pushes the frontier farther back in time, revealing galaxies that are progressively closer to the cosmic dawn. What Z12 and Z13 hinted at, MOM Z14 confirms and amplifies. It shows that the universe's first galaxies were not mere isolated curiosities but may have been more common, larger, and brighter than our previous models suggested. The comparisons also highlight a trend in early cosmic discovery. As JWST continues its surveys, we are uncovering galaxies that defy expectations of size, luminosity, and formation speed. Z12 and Z13 were groundbreaking, but they seem to fit the narrative that the earliest galaxies were relatively small and faint. MOM Z14, by contrast, challenges that narrative completely, indicating that galaxy formation at extreme redshifts may have been more efficient and widespread than the models derived from Z12 and Z13 allowed for. In this sense, MOM Z14 doesn't just break a record, it redefines the cosmic benchmark. It provides a new point of reference for astronomers studying the universe's infancy, offering insights into the speed of star formation, the assembly of mass, and the structural development of early galaxies. Comparisons with Z12 and Z13 help us appreciate just how remarkable MOM Z14 is. It's not just older, it's unexpectedly bright, large, and mature, revealing that the first generations of galaxies could achieve significant development far sooner than previously imagined. Moreover, MOM Z14 highlights the power of JWST to continually extend the reach of human observation. Each successive discovery, from Z12 to Z13 to Z14, underscores how much more of the early universe remains to be explored. While Z14 currently holds the record, it is entirely possible that even older galaxies are waiting to be discovered, just beyond the limits of current observations. This progression emphasizes that our understanding of cosmic history is far from complete and that each new record holder, like MOM Z14, opens doors to questions we never thought to ask before. By surpassing Z12 and Z13, MOM Z14 not only becomes the oldest confirmed galaxy but also the clearest evidence that the universe's earliest structures formed rapidly and efficiently. It sets a new standard for what we consider the cosmic dawn and challenges astronomers to rethink timelines, models, and assumptions about how quickly the universe became populated with galaxies capable of shining across billions of light-years. In many ways, MOM Z14 is the culmination of a journey that began with Z12, progressed through Z13, and now reaches further back than we ever imagined possible. Observing MOM Z14 provides an unparalleled perspective on the sheer scale of the universe, both in space and in time. When we look at this galaxy, we are not just peering across billions of light-years of distance. We are looking back in time to a moment so early in cosmic history that almost everything familiar to us today, stars, galaxies, planets, even the Milky Way itself, did not yet exist. Its light began its journey 13.5 billion years ago, just 290 million years after the Big Bang, a period when the universe was in its absolute infancy. To put this into perspective, the Milky Way, the galaxy that houses our solar system, did not form until roughly 1 to 2 billion years after the Big Bang. That means when the photons we now observe from MOM-Z14 were emitted, our own galaxy was still hundreds of millions of years away from forming. Entire cosmic structures that we take for granted today, galactic clusters, spiral arms, planetary systems, were non-existent. Space itself was a largely featureless expanse of hydrogen and helium, punctuated only by the first glimmers of stars beginning to ignite. By observing MOM-Z14, we are witnessing a universe so young that even our galactic home was yet to come into being. The scale involved here is almost impossible to intuitively grasp. The light from MOM-Z14 has traveled across 13.5 billion light-years, moving through an ever-expanding cosmos. The universe was smaller then, denser, and hotter. Space itself has stretched enormously over the past 13.5 billion years, meaning that while the galaxy's light has taken that entire span of time to reach us, the actual distance to the galaxy now is much greater due to cosmic expansion. This intertwining of distance and time illustrates one of the most profound aspects of astronomy. Observing distant objects is effectively like observing history in action. MOM-Z14 is not merely far away. It is a time capsule, preserving a record of what the universe looked like in its earliest chapters. Consider how different the universe was at that time. The cosmic microwave background, the afterglow of the Big Bang, had already cooled to a few thousand degrees Kelvin, and the first neutral hydrogen clouds were beginning to collapse into stars. There were no planets, no complex chemistry beyond hydrogen and helium, and certainly no life. By the time the light of MOM-Z14 reaches us, we are observing the universe at a fraction of its current age, a universe just beginning to emerge from darkness into structure and light. Every photon from MOM-Z14 is a messenger from a formative era, conveying information about conditions, processes, and structures that existed long before the familiar cosmos we inhabit came into being. This perspective also highlights the enormous temporal scale of cosmology. Human lifetimes, civilizations, and even the entire history of our planet are minuscule compared to the vast ages involved. While we often think of galaxies and stars as timeless, observing MOM-Z14 reminds us that these structures have lifetimes, histories, and evolutionary paths spanning billions of years. We are privileged to witness one of the earliest points along that continuum, seeing the universe at a stage when its story was just beginning to unfold. In terms of spatial scale, the universe at the time of MOM-Z14 was much smaller, meaning that galaxies were closer together than they are today. Gravity was already gathering matter into the first clusters and proto-galaxies, but these early systems were still forming the networks of filaments and voids that define the cosmic web. Observing MOM-Z14 allows astronomers to study these early structures, giving insight into how the large-scale arrangement of the universe developed over billions of years. Furthermore, looking at MOM-Z14 emphasizes the continuity of cosmic history. From this ancient galaxy, through the formation of the Milky Way, the birth of the Sun, the emergence of life on Earth, and the evolution of human civilizations, we can trace a continuous chain of cosmic events. MOM-Z14 represents the opening act of this immense story, and by observing it, we can begin to understand how the universe transitioned from simplicity to the vast complexity we see today. In short, the scale of the universe revealed by MOM-Z14 is both humbling and awe-inspiring. It forces us to confront the enormity of space, the depth of cosmic time, and the youth of everything we consider familiar. Looking at this galaxy is akin to peering across almost the entire lifespan of the universe, seeing not only light from an incredibly distant location but also from an era predating everything we recognize, including our own galaxy. MOM-Z14 provides a tangible connection to the universe's earliest moments, a beacon illuminating the immensity of both space and time. MOM-Z14 isn't just remarkable for its age, distance, or brightness. It may also hold clues about the very first generation of stars ever formed in the universe, the so-called population 3 stars. These stars are believed to have ignited when the universe was still in its infancy, composed almost entirely of hydrogen and helium, the primordial elements created during the Big Bang. Unlike later generations of stars, which contain heavier elements like carbon, oxygen, and iron formed in previous stellar explosions, population 3 stars were pristine, unpolluted, and incredibly massive, burning hotter and brighter than most stars we see today. MOM-Z14 could provide the first direct observational window into this longer-horized, yet never conclusively observed, stellar population. The significance of population 3 stars cannot be overstated. They were the universe's first furnaces, initiating nuclear fusion and producing the first heavier elements necessary for the formation of planets, life, and the complex chemistry we observe today. Without them, subsequent generations of stars, and ultimately galaxies like the Milky Way, could never have formed in their observed abundance. If MOM-Z14 contains population 3 stars, it is not only a record holder in terms of age and distance, but it is also a laboratory for understanding the universe's earliest chemical evolution. One reason astronomers suspect that MOM-Z14 may host population 3 stars is its extreme brightness. Early theoretical models predicted that the first galaxies would be dim because only a few stars would exist at such a young cosmic age. Yet MOM-Z14 shines far more intensely than expected, suggesting that it may contain massive stars forming in rapid succession, or stars that are individually far more luminous than their later generation counterparts. This is consistent with what we expect from population 3 stars: enormous, hot, and short-lived, radiating vast amounts of energy in ultraviolet light, the very light that, after 13.5 billion years of cosmic expansion, reaches us today as infrared. Population 3 stars are also thought to have very short lifespans, often only a few million years, due to their extreme masses. Their deaths likely produced the first supernovae, spreading newly formed heavier elements into the surrounding interstellar medium. This process seeded subsequent generations of stars, leading to the gradual enrichment of the universe and the eventual formation of planets and complex chemistry. Observing MOM-Z14 gives astronomers a unique opportunity to study the aftermath of the first stellar generations, to see how the earliest stars influenced galaxy formation, and to track the chemical evolution in real time across cosmic history. JWST's spectroscopic capabilities are essential for this investigation. By analyzing the specific signatures of hydrogen and helium in MOM-Z14, astronomers can look for the absence or extreme paucity of heavier elements, which is one of the hallmarks of population 3 stars. Detection of these signatures would provide strong evidence that some of the galaxy's stellar population is truly primordial. Even subtle deviations in the spectral lines can reveal the presence of slightly enriched stars, giving scientists a timeline of how quickly chemical elements began to accumulate in the first galaxies. Another fascinating aspect of population 3 stars in MOM-Z14 is their potential impact on the galaxy's luminosity and evolution. These massive stars would have contributed disproportionately to the galaxy's overall brightness, especially in ultraviolet light, which gets redshifted into the infrared by the time it reaches us. Their intense radiation could have driven powerful outflows, influencing the surrounding gas and accelerating star formation in nearby regions. In this way, population 3 stars wouldn't just be passive members of the galaxy. They could actively shape its structure, star formation rate, and chemical composition, providing a dynamic, formative environment within MOM-Z14. Finally, detecting or even inferring the presence of population 3 stars in MOM-Z14 is a major milestone in astronomy. Until now, these stars had remained theoretical, predicted by models but never directly observed. If JWST observations confirm their existence within MOM-Z14, it would mark the first time humans have glimpsed the universe's earliest stars, bridging the gap between theory and observation. MOM-Z14 would then become more than a distant galaxy. It would be a time capsule of the universe's first light, revealing the origins of stars, galaxies, and ultimately, everything we see around us today. In essence, the stars inside MOM-Z14 may tell the story of how the universe first lit up, transforming from a dark, featureless expanse into a cosmos teeming with light, structure, and complexity. Observing these early stars allows astronomers to study the beginning of stellar evolution, the first chemical enrichment of the universe, and the processes that set the stage for all subsequent cosmic history. If confirmed, MOM-Z14 could provide humanity's first direct glimpse of the universe's first stellar generation, a profound achievement in our quest to understand the origins of everything. The discovery of MOM-Z14 would have been impossible without infrared observations, highlighting one of JWST's most revolutionary capabilities. To understand why infrared vision is so crucial, it helps to remember a fundamental truth about the expanding universe. Light from extremely distant galaxies gets stretched over billions of years, moving it from the ultraviolet and visible spectrum into the infrared. By the time it reaches Earth, the light emitted by galaxies like MOM-Z14 is no longer visible to traditional telescopes. It is redshifted far beyond the range of human sight and even beyond the detection capabilities of instruments like Hubble, which, while groundbreaking, is optimized for visible and near-infrared light. Infrared light is essentially light at longer wavelengths, beyond what the human eye can detect. This is critical for observing the earliest galaxies because the universe has been expanding since the Big Bang, stretching the wavelengths of emitted light in proportion to their distance. For MOM-Z14, which exists at a redshift of about 14, this stretching is extreme. The ultraviolet light produced by its young, hot stars has been elongated over 13.5 billion years into the infrared. Without instruments sensitive to these wavelengths, MOM-Z14 would remain completely invisible, lost in the vast cosmic darkness. JWST's near-infrared camera, NIR-CAM, and other infrared instruments are designed specifically to capture this faint, stretched light. They can detect extremely low-energy photons and differentiate them from background noise, allowing astronomers to pick out galaxies that would otherwise be undetectable. Essentially, JWST transforms the universe's most ancient light into a visible signal, providing a direct line of sight to the cosmic dawn. Without this capability, we would have to rely on indirect methods or theoretical predictions to infer the existence of galaxies like MOM-Z14. Infrared vision is also critical because early galaxies are often faint and diffuse. Even if their light were not stretched into the infrared, their intrinsic brightness is still orders of magnitude weaker than nearby galaxies. Traditional optical telescopes struggle to detect these faint signals against the bright foreground of nearer stars and galaxies. JWST's infrared sensitivity allows it to distinguish these ancient sources, isolating the faint glow of galaxies from the noise of closer, brighter objects. This is why MOM-Z14 was first identified as a faint red smudge in NIR-CAM images. It was only visible in the infrared filters that capture the red-shifted light of the early universe. Another advantage of infrared observations is their ability to penetrate cosmic dust. Many early galaxies contain clouds of dust and gas, which absorb visible light but allow infrared light to pass through. JWST can peer through these dusty regions, revealing the stars and structures hidden within. MOM-Z14 may contain such dust and gas, and without infrared imaging, these formative structures would remain obscured. Infrared observations therefore provide not just a view of the galaxy's light, but also a window into its internal structure and star-forming regions. Infrared data also allow astronomers to measure critical properties of early galaxies, such as their stellar populations, star formation rates, and chemical compositions. By comparing light across multiple infrared wavelengths, scientists can determine how many stars are forming, what types of stars are present, and whether primordial elements like hydrogen and helium dominate the galaxy, information that is essential for identifying potential population 3 stars. These measurements are impossible with optical observations alone because the relevant light has been redshifted out of the visible spectrum. Without JWST's infrared vision, MOM-Z14 would not just be faint, it would be invisible. The telescope effectively acts as a cosmic time machine, allowing us to see light from the universe's earliest galaxies that has traveled across billions of light-years and has been stretched into a wavelength that ordinary telescopes cannot detect. By capturing this infrared light, JWST makes it possible to study galaxies in the first few 100 million years of cosmic history, giving scientists a direct view of the universe's formative processes. In summary, JWST's infrared capabilities are not just a technical convenience, they are fundamentally essential for the discovery and study of galaxies like MOM-Z14. They allow astronomers to see the earliest light in the universe, to detect galaxies that are faint, distant, and redshifted beyond the reach of conventional telescopes, and to study the formation and evolution of the first stars and galaxies in unprecedented detail. Without infrared observations, the story of MOM-Z14, its stars, its structure, and its place in cosmic history would remain hidden, and our understanding of the early universe would be far less complete. The name JADES, short for the JWST Advanced Deep Extragalactic Survey, represents one of the most ambitious observational campaigns ever undertaken to study the earliest galaxies in the universe. It was this very survey that led to the discovery of MOM-Z14, making it not only a technical achievement but also a testament to decades of careful planning, collaboration, and scientific foresight. Understanding why this survey exists and how it operates provides valuable context for appreciating the significance of MOM-Z14. JWST was conceived as a deep-field survey aimed at observing some of the faintest, most distant galaxies in the cosmos. Its primary goal is to probe the universe during the first billion years of cosmic history, a period that had remained largely uncharted due to the limitations of previous telescopes. While instruments like Hubble provided glimpses of early galaxies, they could not penetrate the extreme redshifts or detect the faint infrared signals from the universe's earliest structures. JWST, with its unprecedented sensitivity in the infrared, enabled JWST to explore this frontier with clarity and precision never before possible. The survey involves observing carefully selected regions of the sky for extended periods of time, sometimes accumulating tens to hundreds of hours of exposure per field. These deep observations allow astronomers to detect galaxies that are both extremely faint and extremely distant, capturing light that has traveled for billions of years. By combining NIR-CAM imaging with NIR-SPEC spectroscopy, JWST can not only locate candidate galaxies like MOM-Z14 but also confirm their distances and analyze their properties in detail. This combination of deep imaging and spectroscopy is what makes the survey so powerful. It transforms mere detection into a comprehensive understanding of the universe's earliest galaxies. JWST is also designed to be systematic and statistically robust. Instead of focusing on a handful of extraordinary galaxies, it surveys large enough volumes of space to provide a meaningful census of early galaxies. This approach allows scientists to answer questions about galaxy formation rates, luminosity distributions, and the evolution of structure across cosmic time. Discoveries like MOM-Z14 emerge from this systematic methodology. The survey doesn't just stumble upon these galaxies, it is engineered to find them in a way that produces reliable, verifiable data. The name JWST itself evokes something precious and rare, much like the galaxies it seeks. These earliest galaxies are not merely distant objects, they are priceless records of the universe's infancy, fossils of cosmic history that carry invaluable information about the first stars, the formation of structure, and the chemical evolution of the cosmos. MOM-Z14 exemplifies the goals of JWST perfectly. It is a rare, luminous, and ancient galaxy whose detection provides profound insights into the universe's formative years. Furthermore, JWST is the result of international collaboration, bringing together astronomers, engineers, and data scientists from multiple institutions around the world. This collaborative effort ensures that the survey can not only detect high redshift galaxies but also perform the detailed analyses necessary to understand them. Without the coordinated effort of the JWST team, the detection and confirmation of MOM-Z14, along with its characterization in terms of brightness, size, redshift, and potential stellar populations, would not have been possible. In practical terms, JWST operates as a pipeline of discovery. First, deep-field NIR-CAM images highlight candidate galaxies, faint red smudges that could potentially be ancient high-redshift objects. Next, NIR-SPEC and other spectroscopic instruments measure their redshifts and chemical composition, confirming which galaxies truly belong to the universe's earliest epochs. Finally, astronomers analyze these observations in the context of theoretical models to understand star formation, galaxy evolution, and cosmic structure. MOM-Z14 emerged from this pipeline as a clear, high-confidence example of a galaxy formed during the first few 100 million years of cosmic history. In essence, the discovery of MOM-Z14 is not just about a single galaxy. It is a testament to the design and vision of JWST. The survey exemplifies how careful planning, advanced instrumentation, and methodical observation can unlock the deepest mysteries of the universe. JWST was created to answer some of the most profound questions in cosmology, and the identification of MOM-Z14 demonstrates that it is fulfilling that mission spectacularly, revealing the universe at a stage we have never been able to see before. MOM-Z14 is more than just a galaxy. It is a monument to the limits of human achievement, technological, observational, and intellectual. Its discovery pushes the boundaries of what we thought was possible in astronomy and challenges our understanding of the universe in profound ways. Observing such an ancient and distant galaxy requires instruments of extraordinary precision, analytical methods that can extract faint signals from cosmic noise, and an imagination capable of conceiving of objects that existed when the universe itself was barely a toddler. From a technological standpoint, MOM-Z14 represents the culmination of decades of innovation. JWST, the telescope that enabled its discovery, is the most complex and powerful space telescope ever built. Its instruments, particularly NIR-CAM and NIR-SPEC, had to achieve sensitivity and precision far beyond what was previously possible. Detecting MOM-Z14 required isolating extremely faint infrared light, distinguishing it from background noise, and accounting for instrumental and thermal effects that could easily mask or distort the signal. The fact that these instruments performed flawlessly enough to capture light emitted over 13.5 billion years ago is a testament to human engineering on an unprecedented scale. Every observation of MOM-Z14 is a demonstration of how far technology has come in enabling us to reach into the universe's most distant past. From an astronomical perspective, MOM-Z14 pushes the limits of what we thought galaxies could be at such an early stage. Its brightness, size, and apparent maturity defy previous models of early galaxy formation. Scientists expected the first galaxies to be small, dim, and barely formed, yet MOM-Z14 is large, luminous, and relatively structured, suggesting that galaxy assembly and star formation occurred at a pace far faster than predicted. This forces astronomers to reconsider fundamental aspects of cosmology: how quickly gas cooled and formed stars, how massive the first stellar populations could be, and how efficiently galaxies could assemble in the primordial universe. MOM-Z14 challenges not just existing models but the assumptions underlying them, opening entirely new lines of inquiry into the early universe. On a more conceptual and imaginative level, MOM-Z14 stretches the boundaries of human perception. Observing this galaxy is akin to looking back in time to the universe's infancy, seeing a cosmic environment so alien that it existed long before our Milky Way, our solar system, and even the elements necessary for life as we know it had formed. It is difficult to truly fathom what it means to witness light that has traveled 13.5 billion years, emitted by stars that may no longer exist, from a galaxy that existed when the universe was less than 2% of its current age. MOM-Z14 transforms abstract cosmological theory into tangible reality, allowing us to visualize and comprehend a universe that existed at the threshold of time itself. MOM-Z14 also pushes the limits of observational strategy. Detecting such a distant object is not a matter of pointing a telescope at the sky. It requires carefully planned deep-field surveys, such as JWST, which combine long exposure times, multiple filters, and precise spectroscopic follow-ups. These methods are at the cutting edge of astronomical research, integrating complex data analysis, sophisticated modeling, and careful cross-verification to ensure that a faint infrared signal is truly an ancient galaxy rather than a spurious detection or closer object masquerading as a high redshift source. The successful detection and confirmation of MOM-Z14 illustrates the synergy between technological innovation and scientific methodology, showing how human ingenuity can extend our reach across both space and time. Furthermore, MOM-Z14 challenges the limits of theoretical imagination. It forces cosmologists to reconsider the speed and efficiency of star and galaxy formation, the role of population 3 stars, and the early processes that shape the universe's chemical and structural evolution. It asks questions we were only beginning to pose. Could galaxies form this quickly? Were the earliest stars brighter and more massive than we expected? How uniform was early cosmic evolution? Each of these questions pushes the boundaries of our understanding, prompting scientists to develop new models and simulations that can accommodate observations as extreme as MOM-Z14. In essence, MOM-Z14 is a benchmark for the limits of human exploration. It demonstrates that our technological tools are capable of detecting the faintest whispers of the universe's infancy, that our scientific models must evolve to match observational realities, and that our imagination must expand to incorporate phenomena far outside the scope of everyday experience. It is a galaxy that exists at the intersection of technology, theory, and wonder. A reminder that the universe is far larger, older, and more complex than we ever imagined, and that human curiosity, ingenuity, and perseverance can bring even its most ancient corners into view. The discovery of MOM-Z14 has opened a floodgate of scientific questions, challenging astronomers and cosmologists to rethink some of the most fundamental assumptions about the early universe. Its existence, brightness, and maturity raise puzzles that go far beyond simply finding a record-breaking galaxy. They demand new models, fresh hypotheses, and a reconsideration of the physics governing the first few 100 million years of cosmic history. One of the first questions is how galaxies could grow so fast. Traditional models predicted that early galaxies formed slowly, gradually accumulating gas and forming stars over hundreds of millions of years. Yet MOM-Z14 is large, luminous, and well-structured at just 290 million years after the Big Bang. How could such a massive galaxy assemble so quickly? Were there mechanisms in the early universe that allowed gas to collapse into stars at rates far exceeding prior expectations? Could interactions with neighboring protogalaxies or higher densities of dark matter have accelerated the growth of early galaxies? These questions strike at the heart of our understanding of cosmic evolution and force theorists to rethink the timeline of galaxy formation. Another crucial question concerns the first stars themselves. Astronomers have long hypothesized the existence of population 3 stars, massive, bright, and composed almost entirely of hydrogen and helium. Could MOM-Z14 contain such stars? And if so, were they larger and more luminous than previously believed? The extreme brightness of MOM-Z14 suggests that early star formation might have been both more rapid and more intense than models predicted. If population 3 stars were indeed enormous and short-lived, they could have contributed disproportionately to the galaxy's luminosity, reshaping our understanding of early stellar populations and their impact on galaxy evolution. Scientists are also asking why MOM-Z14 appears so well developed structurally. Many models of early galaxies assume they would be small, irregular, and clumpy. Yet MOM-Z14 seems coherent and relatively organized. What physical processes allowed a galaxy to achieve this level of development so quickly? Did early galaxies undergo more efficient star formation, more effective gas cooling, or stronger gravitational clustering than previously assumed? Understanding these processes could revolutionize our theories of galactic assembly and the timeline of cosmic structure formation. The discovery also raises questions about the chemical evolution of the early universe. If MOM-Z14 contains or has produced population 3 stars, how quickly did these stars enrich the interstellar medium with heavier elements? Were the earliest galaxies capable of creating pockets of enriched gas that accelerated subsequent star formation? These questions touch on the origins of the elements essential for planets and life, linking the formation of the first galaxies directly to the long-term evolution of the cosmos. Another line of inquiry concerns the frequency and distribution of early galaxies. Is MOM-Z14 an outlier, a rare cosmic anomaly, or is it part of a larger population of massive, luminous galaxies at extreme redshift that we have only just begun to detect? If such galaxies are common, the early universe may have been far more dynamic and complex than previously thought, with widespread, rapid star formation and galaxy assembly occurring simultaneously across vast regions of space. Finally, the discovery prompts reflection on cosmic timelines and the physics of the early universe. Could there have been processes accelerating galaxy growth that our current models do not account for? Were conditions in the early universe, such as gas density, temperature, and dark matter distribution, conducive to unusually rapid galaxy formation? MOM-Z14 challenges cosmologists to explore whether the fundamental laws of physics, as applied in the universe's first few 100 million years, operated differently or more efficiently than previously simulated. In essence, MOM-Z14 is not just a discovery, it is a series of provocations. Each characteristic of the galaxy, its brightness, size, structure, and potential population of first-generation stars, forces astronomers to ask new questions and reconsider old assumptions. The galaxy serves as a living laboratory for understanding how the earliest cosmic structures formed, how stars ignited, and how galaxies evolved into the complex systems we see today. It is both a record and a mystery, guiding scientists toward answers while simultaneously revealing the gaps in our knowledge of the universe's formative years. The discovery of MOM-Z14 is just the beginning of a new era in cosmic exploration. While it currently holds the record as the oldest confirmed galaxy, astronomers fully expect that it will not hold this title forever. JWST's unprecedented sensitivity and infrared capabilities are opening doors to regions of the universe that have never been observed before, and scientists anticipate that even earlier galaxies may soon be found, possibly pushing our view closer to the very moment of the Big Bang itself. JWST's ongoing surveys, including deep-field projects like JADES and other programs, are designed to scan vast regions of the sky for faint, red-shifted light that signals the presence of extremely distant galaxies. By combining long exposure times with advanced infrared detectors, astronomers can detect objects that are not only fainter than MOM-Z14 but also potentially formed earlier in cosmic history, at even higher redshifts. Each new survey increases the likelihood of finding galaxies at redshifts of 15, 16, or beyond, pushing the limits of what we thought possible in the first few 100 million years of the universe. Future discoveries will also build on the lessons learned from MOM-Z14. Scientists now know what to look for: faint red smudges in deep-field infrared images that could be candidate galaxies from the cosmic dawn. They can use refined algorithms to identify these targets, prioritize them for spectroscopic follow-up, and confirm their distances with high precision. The methods used to detect and verify MOM-Z14 provide a template for discovering even earlier galaxies, ensuring that each subsequent find is more accurate and scientifically valuable. One of the most exciting prospects is the potential to observe galaxies that formed even before the reionization epoch, a period when the first stars and galaxies began ionizing the surrounding hydrogen and making the universe transparent to light. Discovering galaxies at redshifts higher than MOM-Z14 would allow astronomers to study the universe during its most mysterious phase, when the first structures were emerging from a primordial darkness. These observations could provide insights into how quickly star formation began, how massive the first galaxies were, and whether there were bursts of stellar activity that accelerated the early evolution of the cosmos. JWST will also enable astronomers to study the population statistics of the earliest galaxies. By finding more galaxies at or beyond Z14, scientists can determine whether MOM-Z14 is a rare outlier or representative of a larger population of ancient galaxies. This, in turn, informs models of galaxy formation and evolution, allowing researchers to better understand the frequency, size, luminosity, and star formation rates of early galaxies. Each new discovery will help refine theories and provide critical data points for simulations of the early universe. Moreover, future observations will expand our knowledge of primordial stars and early chemical enrichment. If galaxies beyond MOM-Z14 are found, they may contain population 3 stars or even earlier stellar populations. By analyzing their light, astronomers can trace the origins of the first elements, the formation of the first star clusters, and the mechanisms by which galaxies assembled in the first few 100 million years. This deepens our understanding not just of galaxy formation, but of the birth of the elements themselves, connecting cosmic history to the very building blocks of matter. Beyond the science, the ongoing search for galaxies beyond MOM-Z14 also pushes the boundaries of human imagination. Each new discovery is a reminder of how vast, old, and dynamic the universe truly is. It challenges our sense of scale, our perception of time, and our understanding of what is possible in the cosmos. JWST's continued exploration promises to reveal galaxies so distant and ancient that they stretch our concepts of the universe, bringing us ever closer to witnessing the cosmic dawn. Ultimately, the story of MOM-Z14 is far from over. JWST will continue to probe the early universe, scanning deeper and more precisely, with the hope of finding galaxies that formed even earlier, before MOM-Z14, and perhaps even catching glimpses of the very first sparks of star formation after the Big Bang. Each discovery will provide new data, pose new questions, and expand our knowledge of the universe's earliest epochs, ensuring that the cosmic story continues to unfold before our eyes. As we reflect on the journey that led to the discovery of MOM-Z14, the enormity of its significance becomes clear. This galaxy is not just a distant speck of light, it is a beacon from the universe's earliest moments, a messenger carrying photons that have traveled for 13.5 billion years to reach us. Through the lenses of JWST, we can study its structure, its stars, and its light, unlocking secrets of galaxy formation, star evolution, and cosmic history that were once the realm of theory and speculation. MOM-Z14 challenges our assumptions, expands our understanding, and reminds us of the incredible complexity and dynamism of the early universe. Every aspect of MOM-Z14, its brightness, size, structure, potential population of first-generation stars, and place in cosmic time, tells a story about how the universe came to be. It provides a rare glimpse into a period when the cosmos was in its infancy, when stars first ignited and the first galaxies began to assemble from primordial gas. Observing MOM-Z14 allows us to witness the processes that ultimately led to the formation of galaxies like the Milky Way, the creation of chemical elements necessary for planets, and the conditions that eventually made life possible. It is a tangible connection to the beginnings of everything we know, a bridge across billions of years of cosmic evolution. Moreover, MOM-Z14 is a testament to human curiosity, ingenuity, and technological achievement. Its discovery showcases how far we have come in our quest to understand the universe, from early theoretical models to advanced instruments capable of detecting the faintest signals from the cosmic dawn. JWST and surveys like JADES demonstrate that through ingenuity, collaboration, and persistence, we can reach across space and time to observe events that occurred when the universe itself was barely 2% of its current age. By pushing the boundaries of observation and theory, JWST inspires both scientific inquiry and wonder. It forces us to confront profound questions about the origins of galaxies, stars, and matter, while also reminding us of the vast scale and age of the cosmos. The galaxy serves as a symbol of exploration, revealing that even the most distant and ancient corners of the universe can be brought into the realm of human understanding. In the end, the true power of JWST lies in perspective. It connects us to a time before the Milky Way, before the formation of the Sun, before the Earth, and before life itself. It embodies the universe's first flickers of light and the processes that set the stage for everything that followed. In observing it, we are not merely looking at a galaxy. We are peering into the earliest chapters of existence, tracing the steps that led from cosmic darkness to the structured, vibrant universe we inhabit today. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.